Well, let me kick off then. Thank you, everybody. Good morning, or good evening, or good afternoon, or wherever you happen to be. It's great to see so many people online, and I've been really pleased by the interest that's been shown in this lecture series. My name is Simon Carlisle, and I'm directing the Australian Future Hearing Initiative, which is a Google collaboration with 5 key research partners in the hearing aid and cochlear implant space. And you'll hear more about that in future episodes. So this is the first in a series of lectures that are based around Dick Lyon's book, Human and Machine Hearing, Extracting Meaning from Sound. Now, Dick has been the key technical lead of a hearing initiative project here in Sydney, and the technical centerpiece of which has been his CARFAC model of cochlear processing. Now, Dick's book provides a great foundation for understanding the physiology, engineering, and modelling behind CARFAC. So these lectures represent a wonderful educational opportunity, not only for people working on the project, but also anyone with an interest in hearing science and listening assistive devices in general. A second motivation for these lectures, and this is one dear to my heart, is to bring greater visibility and a broader recognition to some of the great work that Dick Lyon has been doing in the hearing space for decades. As I mentioned in the original announcement of this series, the intention is to cover each chapter in the book using a range of different presenters, with Dick also providing commentary, and he'll be available for Q&A at each lecture. And of course, everybody attending the lecture will benefit from a pre-read of each chapter. And I'm sure the lectures themselves will give rise to plenty of interesting questions and discussion. We'll record these lectures and make them available on the Hearing Initiative website hosted by Macquarie University, so that they become a valuable educational resource for the whole community. I feel very fortunate to have Dick as a colleague, and I'm deeply grateful for the work that he's done and that he is doing. So please welcome Dick for the opening lecture of this series on signal processing for hearing. Over to you, Dick.
Thank you very much, Simon, for that nice introduction, and thank you everybody that showed up today. It's quite an impressive turnout. I'm very happy. So a bit more about the idea for this course. We did this back in 2021 during the pandemic work from home times, and it worked out great having everyone in their little box, and instead of trying to do the kind of hybrid meetings that we had done in some courses before, where it was actually pretty awkward to see who's talking and stuff like that. So if y'all want to be in your own little box in the future, you can. If you'd rather be in a conference room, that's okay too. I'm looking forward to all the students and guests doing all the lecturing, because I didn't want to do all that much work. I wrote the thing after all. So when we did this before, we did a chapter every other week with office hours in between weeks, and that was kind of a leisurely pace and took more than a year to get through the book. I don't want to take that long this time, so we'll be meeting every week, and I'll stick around after the recording ends for a more informal chat in office if anyone wants to. So as Simon said, doing the pre-reading is important. We're not going to try to teach the book in these lectures. We're going to basically have people say what their reactions are, what they discovered, some interesting things they found, some questions that got brought up, or whatever, or alternate ways of looking at the material. Whatever they want to talk about is fine, but don't expect to have that lecture be a substitute for the reading. There's this important link. If you don't actually have the book yet, go to machinehearing.org and search for the word free. You'll also find words like errata and apologies and things like that for some of my more egregious errors. There's a free PDF there, and also links to places where you can buy the book. If you're inside Google, you can look at the resources from the last time we ran this course, including recorded presentations and slide decks and so on, but we haven't made that material available outside to the public. So before I jump into chapter 1, I want to point out that the book has parts, and each part has a dedication. So part 1, about sound analysis and representation overview, the first 5 chapters of the book, is dedicated to my old friend John Robinson Pierce. Here's a picture of him from about 1944, I believe, where he's holding a traveling wave tube amplifier, which is he didn't invent this thing, but as he says, Rudy Kampfner invented the traveling wave tube, and I discovered it. So he basically did the math to help make this thing real, and it's the electronic amplifying element that's still used in almost every communication satellite. So he had quite a career in vacuum tubes, and we'll say more about him later. But when he retired from Bell Labs in 1970, he came to Caltech as a professor when I got there as a freshman. And we were good buds, and he hired me and got me a job and put me in the Bell Labs regime, where I learned about the digital signal processing that's part of the basis of what's in this book. And he went on to do a lot of work in hearing science at Stanford and at Caltech and Stanford. He had a big influence on my approach. And he was quite a character. Not everyone views him favorably for various reasons, but he was quite a character. I'll get into a bit of that later. And then each chapter, I tried to pick some pithy quotes. That was kind of a fun part of finishing up the book, and that in those many years between when it was mostly written and when I finally finished it, I got to have a lot of fun picking quotes and getting all the capital letters right and all that kind of stuff, and which is why I wrote most of it in 2010, but it didn't come out until 2017. So I like this one from 1697 about magic numbers and moving it things. This feels like it's about Tom, that's you making noise. Feels like it's about digital signal processing driving machines or something like that. So I put that one in there. And this other guy in 1838 says it would be in vain, man's skill would be in vain exercise to try to imitate the cochlea. And part of what I want to prove in this book as well, it's not in vain, and the biomimetic approach works, mimicking the biology, the most perfect acoustic or hearing instrument. So yeah, those are just some of the kinds of tidbits I like to throw in. Here's the outline of the chapter. Won't go through this, but starts off with on vision and hearing, a la David Marr. So you might want to know who the heck is David Marr. And he was a MIT professor, sadly died young. He systematized the study of vision and computer vision into different levels, and he called them sometimes function, process, and mechanism, or sometimes computation, algorithm, and implementation. And I have this diagram here from Bill Yost, who basically called these levels function, mode of operation, and anatomy. And what we're after in this endeavor is to understand the function. But to do that, we have to really understand how it works. What are the underlying computations that make it function as it does? And what is the anatomy and physiology that supports that computation? So this is sort of a way to get our head around what we're doing. If you look in the lower right corner there, you see I've put Carfax in a little box here. That's the model of filtering, distribution, and transduction in the cochlea. I haven't done a lot of work in this book on the outer and middle ear, so that's a big hole that we could fill other ways. And the more central processing in the auditory brain, I've written a few chapters about it, but it's mostly a big unknown. So I put the question mark in that box. So there's a lot of words around this stuff in the book. Part of Marr's approach was kind of bottom up and modular, and that's the way I like to do it, being an engineer. People are fond of pointing out that there are massive descending connections in the auditory brain and even all the way up to the cochlea, and those are important. I don't deny them, but I think they're secondary to the bottom-up modular organization. They serve to control attention in some cases, or to optimize parameters in other cases. But the data we have to go on for modeling the system are mostly from animal experiments with bottom-up stuff, and so that's mostly where I've looked. We want to build systems with stable subsystems. This is the way evolution works. In fact, I just saw a new paper out in the news feed today about someone's discovered the laws of evolution, and it has to do with sort of adding functional layers on top of stable functions. So it's an idea that comes around now and then. I'm not going to read all this. I'm just sort of pointing out what some of these topics in the chapter are. There's a lot in the book about time domain versus frequency domain views of things. On the upper right here, we have a guy blowing air through holes in a rotating disc. This is a siren. It makes a tone based on the hole pattern and the speed of rotation and so forth. And August Seebeck did experiments with one of these things and using uneven hole spacing and things like that. He came up with a theory of kind of pitch and timbre kinds of things. About the same time that George Ohm, reacting to Fourier's analysis scheme, came up with the idea that the ear is insensitive to phase, and Hermann von Helmholtz adopted that and basically says it's the frequencies that are present that you care about, not their phases. And he would use these resonators. Helmholtz developed these things called Helmholtz resonators that have a compressibility of an internal volume working against the mass in a neck that causes a resonance, and you can put the little B opening there in the picture into your ear and listen to that resonance. And with this, Helmholtz could hear out any partial tone in a complex musical tone. So he knew they were real. He knew those frequencies were there. But based on that, he kind of made an unreasonable leap to saying that just the amount of each frequency is all you care about, not the phase or anything like that. So there's a lot of, I think, confusion that comes from that, especially when you get outside the realm of musical tones, which was the realm that Helmholtz was mostly confining himself to. So Helmholtz had a theory of the cochlea based on that as essentially a frequency analyzer, and that theory has kind of persisted and come up over and over again in spite of some papers that try to debunk it and so on. I looked in a bunch of sources starting way back about people saying what is the function of the cochlea, and you get things like it's to determine the pitch of a sound, or to receive and appreciate musical sounds, or to appreciate the qualities of a sound. And some of these are better than others. You got the Helmholtz thing in the middle there, that indented quote that says it must be to decompose every waveform into simpler elements according to a different law. And then it receives a sensation from each of these simpler elements. Well, this idea, I think, has caused way more harm than good over the years, so I try to get rid of it. The quote down at the bottom from W. Dixon Ward, 1970, says that for years, musicians have been told that the ear is able to separate any complex signal into a series of sinusoidal signals, that it acts as a Fourier analyzer. This quarter truth, worse than a half truth, known as Ohm's other law, has served to increase the distrust with which perceptive musicians regard scientists, since it is readily apparent to them that the ear acts in this way only under very restricted conditions. Like, if there's really only one tone, maybe you can describe the response that way, but for any realistic sound mixtures, this is such a limiting view that you have to get rid of it. So I put there's a lot in the book in every chapter of trying to figure out what, if we're not doing the simple thing that Helmholtz suggested, what are we doing? That's kind of what the book's about. George von Benkesee was a famous hearing researcher who had a commentary on this as well. He said that dehydrated cats and the application of Fourier analysis to hearing problems become more and more a handicap for research in hearing. I just loved the way he lumped dehydrated cats right in there with Fourier analysis. He had a lot of difficulty with the animal preparations over the years, and he saw that as a problem. But the application of Fourier analysis to hearing problems he saw as an equally bad problem. You might note, if you've read anything about this guy, he was famous for discovering the cochlear traveling wave. He got a Nobel Prize for his work. You might note that he died in 1973, but he had gotten his manuscript in on time, so I got this quote from his posthumous publication on some biophysical experiments from 50 years ago.
I mean, the irony of this quote, Dick, is that von Benkesee used cadaveric humans' ears, right, to study the traveling wave, and missed some of the active processes.
Yeah, his preparations were dead, especially in his early decades. But I think he tried to use some live cat preparations later on. I don't remember exactly how far he got with that. So a better conceptual starting point on cochlear function is what we need. And there's a couple of them here. There's one up in the top paragraph. It says the main function of the cochlea is to translate auditory events into a pattern of neural impulses that precisely reflects the nature and timing of the sound stimulus. I like this because it doesn't say the frequency, the pitch, the loudness. It's about events. It's about things happening in the world. You want to know what's going on around you. And the more kind of doubly functional characterization that John Allen has in the indented quote there, the two main roles of the cochlea are to separate the input acoustic signal into overlapping frequency bands and to compress the large acoustic intensity range into the much smaller mechanical and electrical dynamic range of the inner ear. It's this second function, this compression or automatic gain control function, that gets so often glossed over, not just in studies of hearing, but in most engineering attempts to process sound. People don't think hard enough about how they're going to cope with the huge dynamic range, and they do things that end up being very limited because of that. So there's a lot in the book about that. That's a very there's the two roles that Alan describes here. One is very linear, and the other one's very nonlinear, and we have to get those things to work together. Another important kind of nonlinear effect is what we had from Tartini, among others, back in the 18th century, this observation that you could hear these low notes when two different instruments are playing. The instruments are not interacting with each other in any way. They're like on opposite sides of you, if you like. They're producing nice clean notes that don't have any subharmonics, and yet when you listen to the two of them together, you can hear these low notes. And these, it turns out, these really exist in the ear, and you can pick up these cubic distortion products and things like that as otoacoustic emissions. They're part of what the cochlea does. And you can view it as a diagnostic for proper cochlear function, or you can view it as just an epiphenomenon, a side effect that's not intended or useful. It's just something that happens to go along with the way the cochlear works. And maybe it's both of those things, or maybe it's actually useful. There's also, besides these kind of well-known cubic distortion product tones, there's also the quadratic distortion products, and we'll get into what all that means in a chapter on nonlinear signal processing at some point.
Dick, before you go on, can you give an example of where these distortion products could be of use for the auditory function?
Yeah, in terms of the quadratic distortion, there was kind of long-standing question of whether those are useful in the perception of pitch and musical pitch in particular, because you can, if you mask the low frequency region where those would be generated, you can still hear pitches. But Pattinson and some of his colleagues showed that you actually might get a much better or stronger perception of musical pitch if you allow those quadratic distortion products to be there. So that's one example. The cubic distortion products, I don't know. They may be the right explanation for a lot of musicality in the sense of like the root pitch of a chord is essentially that. But there's other ways you can account for that too. Thanks for asking, Sridhar.
Yeah, thanks for the answer.
So there's several themes in the book that I want to mention. First of all, it's fundamentally an engineering approach to biomimicry. We want to understand how human hearing works so we can build machines that hear better. In the current project on hearing aids, we want to kind of close the loop on that and make these machines help us hear better. But for what I've mostly done with this work over the years, it's like getting computers to understand speech and sound events and music and pitches and cover songs, melodies, all that kind of stuff. So there's some examples of that in the book, and there's not much about hearing aids in the book. There's a substantial section in the last chapter, I think, but that's about it. So within this engineering approach, we develop efficient causal time domain streaming modular bottom-up models, CARFAC plus stabilized auditory images and so on. We model waves as filter cascades, which limits the applicability of the models in some ways. These filter cascades have no backward propagating waves, so they can't model otoacoustic emissions. We can still see the generated cubic distortion tones, but not coming back out as sound, but propagating forward to their place of localization. So to do all this, we need a balance of linear and nonlinear methods, modeling of linear and nonlinear effects. So we also have in the book an emphasis on temporal fine structure, not just short time spectra. So we talk in the part one about kind of conventional approaches like short time Fourier analysis, but then we don't use that anywhere else. Throughout the book, I try to honor my heroes, including some far past ones, and like August Seebeck, who I mentioned, and more recent ones, 20th century old dead guys like Jefferson Licklider, and currently alive guys like Patterson, and so forth. And in a few cases, maybe three or four of the chapters, we've got experimental demonstrations of advantages. I think 3 of the chapters are kind of adapted from previously published peer-reviewed papers where we showed some of these advantages using these methods. Now, we've used mostly shallow machine learning methods. I think you all know that deep learning or deep neural networks are in vogue nowadays. And since I wrote most of the book in 2010, I kind of missed out on that wave. Certainly don't mean to deny it, but the examples show that you can get some advantage even with the old shallow learning methods. And then I've got sprinkled throughout the book a lot of what I call history boxes and connection boxes. Try to draw connections to corresponding techniques and topics in math and statistics, physics, biophysics, different engineering fields and radio and so forth. So the idea here is that people are coming at hearing from so many different directions. They'll bring different terminology, different viewpoints. I want them to see how it connects. So if you're coming from statistics and you're used to generating functions, I want you to understand how that relates to Z transforms and things like that. So that's what a lot of those boxes are about. And then I try to get cute sometimes, like on this little Winnie the Pooh thing, where his concept of extracting meaning from sound is this kind of rational reconstruction of what it means to have a buzzing noise, and what it means for him is there's honey to eat. So I'm not saying this is the right explanation, but the point is that he extracted that meaning. He knows that buzzing sound means there's honey to eat, and this is what I mean by extracting meaning from sound. There'll be different tasks and different kinds of meaning in different tasks, and if you can use sound to solve a problem or make an interpretation that's useful to you, then that's what you're doing. You're extracting meaning. I have a what I call by the book 4-layer model here. Nowadays with machine learning, it's more popular to do what they call end-to-end modeling, where you put in a sound waveform and you train everything and you get out the answer you're looking for. But I believe there's still a lot of value in putting your knowledge in by the way of stable subsystems that extract rich feature spaces and then build the learning on top of that. So the auditory periphery model, that's the CARFAC, and that's pretty stable and useful, and you can you can use it in a way that's analogous to what everyone's still doing in speech recognition and other sound analysis fields, where you just kind of low pass the output and get sort of a short time spectral-like or spectrogram-like representation called a cochleogram, and build everything on top of that. But if you do that, you're missing the opportunity to use the temporal fine structure that the ear sends to the brain. So what I prefer to do is put in another level of kind of stable subsystem there, the brainstem level, where we extract stabilized auditory images. Those are dimensionally richer than a cochleogram or spectrogram, and have more information because they capture not just the short time spectrum, but also more information about the somewhat longer term temporal regularities that represent pitch and harmonicity and so forth. The third level here, the application dependent feature extraction, is one that we could probably just throw out and do levels 3 and 4 in a more end-to-end style. But for the examples in the book, I did this. And then the fourth level was a kind of a shallow learning system. So you can replace 3 and 4 by a deep learning system if you like, and you can integrate 1 and 2 into that and use parameter optimization by backpropagation to tune the parameters of the whole thing without losing the advantage of putting in your knowledge via the structure of those processes. Now, on the right, I show optional top-down feedback paths, and I'm pretty much not using any of these, but I have no objection if someone figures out a good way to use them. In particular, you can think of what the interactions between the thalamus and the cortex in the brain is sort of between 3 and 4 here, where the thalamus is where things get selected based on selective attention, so that the cortex only has to deal with what you're attending to. I think, at least that's the way the vision guys describe it. Down here between 2 and 1, I show efferents. That's where the brainstem controls the cochlea. We do have kind of a functional model of that, but we don't do it by feedback from our level 2. We do it within level 1. And from the cochlea back out to sound, otoacoustic emissions, we don't do that. As I mentioned, we have a kind of a unidirectional wave propagation. So that's kind of the structure in which all the pieces in the book are trying to build up the system theory for describing all these pieces, and then the examples and the history and so forth. Speaking of history, since I whipped through all those slides, we have plenty of time. I can go through these other guys. This is not covered in as much detail in the book, but there's mentions of these guys at various places. John Pierce, I mentioned in the part 1 dedication. He and his buddy Ed David at Bell Labs wrote a couple books on sound for the popular press. You know, back when a Doubleday original cost $1.45. They're pretty nice little books. They're pretty good at popularizing science. Pierce wrote a book on quantum electronics too, by which he meant transistors and lasers. That was pretty cool. And he's written various other books on more technical subjects. He's also written science fiction under the name J.J. Coupling. But in their 1958 paper, Pierce and David commented on the fact that different types of meaning extraction involve different types of processing. And we don't perceive vowels in the same way as gunshots and so on. And they're asking, could we understand enough to make such a machine? And yeah, so that's kind of what we're doing now. It's 65 years later. And on the prospects, they clearly knew it was going to be a long, hard road. And they at the bottom, basically, whether such machines are ever actually built will depend upon how complex they need be. And in essence, how much human time, effort, and money man is willing to expend in simulating human functions. So this was pretty amazing vision, I think. And, I think we know now that with enough generations of Moore's Law, computing has gotten so cheap that the cost of doing these machines is kind of negligible compared to the cost of the human effort that went into doing all the development. But now that's been well repaid and will continue to be well repaid as we make these things better. And yeah, the rate of progress recently with sort of infinitely available computation and deep learning techniques that work has been just astounding. I'm not sure it's a singularity, but it's definitely a sped up process. But you know, what's on the one hand, it's amazing that it took 65 years. You know, they barely had a computer back then, but they had a good view of where computers were going to be going and what they'd be good for. I'm not sure what computers they had by 58, but the first electronic stored program computer to run a program was 1948. So they weren't too far down that path yet. Ed David wrote a paper called Artificial Auditory Recognition and Telephony. So, you know, they understood that the telephone network was a place that would benefit hugely if they could do these things. So I like his dashed line box here in the middle of his diagram, where he talks about a representation of efficient speech transmission. I like it because it's kind of the only place I find in the old literature that really respects the auditory nerve as a key interface. So you can think of that as the interface between our levels 1 and 2. The ear sends to the brain by way of the auditory nerve signals with a lot of temporal fine structure, and the brain does whatever it needs to do to interpret that. So I liked that. I think I put that picture in the book. I'm not sure. Maybe not. They anticipated the automatic speech recognition via methods of learning, big data. It said by observing its own errors, it might, over a period of time, compile a successful set of rules. So, you know, we don't use a rule-based system anymore, but a successful set of weights would be the right substitution there. Identification of spectrographic features might be accomplished similarly. So they like the approach of analyzing how a human being could do it and how a machine could do it, and then making models and testing them experimentally, and the use of computers to simulate the equipment and so on. So this was all very cool. And yeah, Ed David, you know, as I mentioned, John Pierce went on to be a Caltech professor. That was cool. And Ed David went on to be science advisor to President Nixon and head of the Office of Science and Technology Policy. And then he was like chief scientist for Shell Oil, where he became a kind of a global warming denier and started publishing things about how we don't need to worry about global warming. So don't have too many warm, fuzzy feelings about it. Warm, maybe. But they actually did speech recognition. In the upper right here, they've got 3 different rows. The top row, simplified spectrogram, are the dark regions, or where there's energy, and light regions where there's not, for the words 1, 2, and 3. And then the black master and white master below that are patterns that is supposed to indicate where the energy must be and where it must not be. And then they would do pattern matching with these things. And the way they did it was by punching these patterns into punched cards and using card sorting equipment. So you didn't even need a computer, because you could program a card sorter with patch cords and so on to count logical functions of holes in different cards and sort them and so on. So they were able to do speech recognition with punched cards in 1958. So I thought that was pretty heroic. Pretty good hackers. So, and Pierce, well, he went on to kind of torpedo the speech recognition field by this paper. This is one of the things that a lot of people remember him for, and the other one was his work on a committee, some kind of national committee about natural language translation and work in that field, and he kind of torpedoed that too. But this little paper was basically impugning the motivations of people that work in speech recognition, and they're saying they're just in it to have fun and get famous, and they're not really spending our money efficiently or doing anything useful or something like that. It was really crazy, and it generated a lot of good rebuttals and discussion, but also prevented a lot of federal funds from going there. So anyway, I never talked with Pierce about that, but found out about it later. He was also known for this little aphorism, artificial intelligence is real stupidity. And some other, he had a lot of funny sayings. Like he told me one time he tried to get his engineers to make a computer as easy to use as a telephone. He says they finally did it by making a telephone as hard to use as a computer. So anyway, that's just a little historical aside, and I want to leave plenty of time for discussion, because if you've read the chapter, you might have some pieces of it I didn't mention that you'd want to talk about. So let's do that. I think I'll get out of the presentation so I can try to see people. If I can find my way back to the window. Yeah.
That was really fun, by the way.
Oh, good. I didn't see who said that.
As Neil. Hi.
Oh, hi, Neil. Yeah. Well, I hope other people in the other chapters will do fun romps through them as well. There's no need to try to teach the material rigorously. Just tell us your fun reactions or whatever.
Dick, I might open with an observation and get your response. One of the things the chapter did for me was really draw together what the inputs were to the current paradigm in a way that I have been thinking about for quite a while. My own thinking was heavily influenced by Horace Barlow and the work that he did in the 60s on looking at statistics of the visual scene. And obviously, Lewicki in the early 2000s, and then obviously some of the people on this call, I think Jan and David have done work particularly focused on localization, looking at statistics, Fred Unison, of course, and others. And it's when you point out that, where Helmholtz and others were coming from the beginning was actually thinking about musical tonality, and the simplicity of the statistics of that seems to have been what's driven this major paradigm. And even though Horace was more than half a century ago, and indeed it's been 20 or more years since those ideas are being more directly applied to hearing, it takes a lot to shift the paradigm.
Yeah, it does. Yeah, the Structure of Scientific Revolutions book by Thomas Kuhn about paradigms and how they change and so on. Well, my older brother David was a student at Princeton and took the class from Thomas Kuhn where he taught that idea, and my brother told me, no, that's crazy. That's not the way it happens. But I think it is the way it happens. You have to wait for a generation or two to die off for new ideas to really take hold.
Paradigms also shift, when the anomalies build up, and those anomalies then become, socially or economically important. And it might be, for instance, that, as you argue, that the front ends to our listening machines are pretty damn stupid in the extreme, and we can only push those very large deep neural networks to the extent of the statistic that's coming in. So maybe that turns out to be the anomaly that shifts the paradigm. Yeah,
and I'm happy to have people anywhere help me prove that. So that was part of what I was trying to do, trying to prove early on as I did the book. And as I said, we showed some experimental advantages in using stabilized auditory images instead of just short time spectra. But we did that before the era of deep networks, and now we have to go do it again because everyone's got their attention diverted by that.
Yeah. Well, hopefully we'll have great opportunities to do that here in Sydney as part of the Hearing Initiative projects.
Yep.
Let me open up to the floor to other questions and observations.
May I follow up on, Simon, what you were asking in the discussion there?
Yeah,
Please go.
So, yeah, I'm just riffing off the issue of re-examining some of these advantages of using a kind of a realistic auditory front end. So with the deep neural net, give it sufficiently, if it's a sufficiently deep network and you give it sufficiently diverse data, could it work just as well as a model with just using the directly the acoustic inputs versus what you're arguing for, which is that you need a realistic front end to have kind of a rich enough information to feed the computation structures downstream to support the auditory goals that you have. I'm not sure I expressed this very well, but I'm wondering if the deep neural nets could make up for not having a good auditory front end.
Well, yes, maybe. So
Mhm.
the deep network won't make up for loss of information. But if you're asking, could it just take a waveform in and do all the computation and learn how to extract information without the aid of these engineered levels? Absolutely, that's possible, because you could put in a structure that's capable of learning these structures, and if the training and optimization works, then it will behave no worse than what we engineered by hand, right? So we've done some experiments along those lines. A number of people have experimented with waveform input networks to do various sound tasks. And generally the result has been they get kind of close to what the engineered approaches would do, but they haven't beat it. The first guy I know of that beat it was Neil Zegeter when he was a PhD student. He's now an ex-Googler. But when he was a PhD student, he engineered a multi-layer network that would take a waveform in, and it would do within the network, he engineered layers that you could think of as doing kind of a fairly simple auditory model. That is, instead of just learning a bunch of convolutional weights and hoping it would learn nice filters, he actually parameterized nice Gaussian filter shapes by their widths and center frequencies. And then instead of just doing a logarithm for compression, he implemented our per channel energy normalization idea and learned parameters for that and so forth. He trained it and tested it on a variety of tasks and showed that it worked better than the log-mel baseline front end that he started with. So to Neil, it was a triumph of end-to-end learning. And to me, it was a triumph of putting our auditory knowledge into a network. So I actually made him a bet. I said, I bet I could pick parameters by hand for your network that would work better than the ones you learned. Short story, I lost the bet, but I came real close. On most tasks and architectures, there was not a significant difference, but on a couple of them, his optimized thing beat me. But then he went on to show that if he started with my values and optimized from there, it would do even better. So, from my point of view, I won, even though it cost me a bottle of whiskey. John Pierce had another great quote. He said, back when he bet Jim Early he couldn't make a transistor run at 30 megacycles per second. Later said, that was the best bet I ever lost. He lost a bottle of scotch. So that was my model. Sometimes you want to make bets you can lose.
I could just say on that note, while I agree with Dick, you can get there, but the problem with dumping it blindly into the machine learning algorithm is you've got no knobs left to make adjustments when you try to productize it, right? And that's, it'll work great in the lab maybe, but you can't make a product out of it unless you've got some way to make adjustments for the realities of putting something. And then there's a question of efficiency, right? And that's probably a couple orders of magnitude.
Yeah, and we just went through that with some of the modeling work where replacing a big finite impulse response convolution with an efficient filter picked up a couple orders of magnitude in execution speed. Well, it's the same way in these filter bank front ends. If you use an efficient IIR filter structure, there's a whole lot less work to be done than if you just throw a big, huge convolutional layer at your waveform. So yeah, efficiency is part of it, but the ability to learn in these big parameter spaces is another. And as I said, nobody really succeeded at doing that until Neil constrained the parameterization to a particular shape of filter. And it wasn't, Gaussian filters were not ideal filters for the job, but they were at least constrained enough that you could learn their parameters and do well. Hey, Tim.
Hey, how's it going?
Good.
I wanted to ask about earlier on you were talking about the frequency or the cochlea as a frequency analyzer has done more harm than good. And I was just thinking it might be fun if you had some examples of harmful times where it did do harm.
Oh, well, not to pick on your company, but there's one.
Okay, well, yeah, well, let's just address that head on. So like all cochlear implants use a frequency analyzer at their front end to determine what the stimulation pulses should be.
Yeah,
back at an electrode level.
Back in the early days in the 70s, I think the first cochlear implants that were good enough for a person to understand speech were single channel, or the only thing they had was time domain. They had no frequency to place mapping. And so that's been thrown out. And so I'm not saying there's no important frequency to place mapping, but just throwing out the time domain is where it has done harm.
Mm-hmm. Yeah, I guess that compared to those single channel timing based ones, though, speech perception with these new cochlear implants is much better.
Yeah, for most people, yeah. And
but
when signal to noise ratio is high enough, yeah.
Mm-hmm.
But it's not a binary question either, is it? It's not one or the other. It's how do we draw these paradigms together?
It's like John Allen's thing on the function of the cochlea is to separate the waveform into overlapping frequency bands. Well, yeah, you can call it a frequency analyzer, but that's not. It's not analyzing in the sense of reporting what frequencies are present, which is the way a lot of people think of it, and more or less the way it's implemented in cochlear implants, where you pick some discrete subset of locations to stimulate and forget about the time pattern. So we'll work on that.
Cool. Thanks, Dick.
Dick, I have a question. So, do you think there is anything special to the audio front end for robots? I'm asking because I searched for the whole book, and there's no mention of robots whatsoever. And obviously, a robot is kind of a machine.
Yeah, definitely.
In your chapter 1.7, you mentioned your dog. Actually, it reads, my dog is pretty good at processing sounds too. So if her practical application is to greet someone at the front door, she gets the information she needs from the sound, or either a knock or the doorbell. So to me, this is pretty good description of how intelligent agents react to sound.
Yeah, definitely.
Yeah.
Yeah, I mean, I didn't get into robots specifically. They have some unique problems like suppressing the noise from their own motors and so on, which I'm sure you're familiar with. But yeah, that's certainly included among the kinds of machines I'm talking about. The things we have around our house that interpret sounds, whether they're mobile or not, whether they can, get me a beer or not. Yes, they're included.
Okay. Thank you.
And thanks for coming, Schwan, and for volunteering to present a chapter.
Yeah, always happy to.
Yeah, I have a somewhat related question. Because of the dog example there, I was just wondering, like the human voice, like how much does the human voice really influence the evolution of the human hearing system? I mean, and is it so much that it's kind of worth modeling them in tandem and sort of constraining the human hearing system model because of the human voice? And if so, I mean, is this discovered due to comparisons with animal hearing systems, that kind of thing?
Yeah, there's good books on the evolution of vertebrate hearing systems and stuff like that. And basically all the lower levels are stable and relatively unchanged, relative to cats and dogs and ferrets and chinchillas and all these other experimental animals that are used in the field. The cochlea and brainstems, not that different. Where the human brain differs is in the specialized cortical structures for understanding speech. So that I would put up at level 4. So whether you're building a system to do speech or music or bird song or whale noises or whatever, the lower levels shouldn't much depend on that. We've got some good good examples of systems in bioacoustics using some of the kind of simplified auditory approach things, like the per channel energy normalization is sort of like the cochlear automatic gain control that I teach. It's kind of a poor man's version of it, but that was found to give good advantages in both the whale detection and the birdsong classification projects. Those have been published on. So yeah, they're not speech specific, and I tried not to get very speech or music specific in this book, because those if we can get the basic sound representation right, then there's plenty of people that will I think apply that and show progress with their much more elaborate speech and music tools.
Yeah, thanks. That makes sense. Yeah.
So everyone, I see that we're coming up on time. We might have time for one more quick question for Dick.
I had a question about or more like a comment on like relegating feedback to be a secondary effect. And I think you mentioned that this is also driven by the animal models, right, which inspire or motivate. Like that's where the data is coming from that we're using to model the periphery. But would you consider also data from like behavioral or EEG style studies, which could take more attentional feedback, right? Which would be, I believe, more relevant for a hearing system, like in hearing aid. So I just felt a little off put by a feedback is secondary. So I just wanted to,
It's secondary in my approach. I don't mean it's unimportant, but definitely when we can get more data from things like the electrocorticography and the EEG and so on. And I know you've probably worked on the attention stuff with the neuromorphs, right?
Yeah, that's what I've been excited about. So I was like, hey, I love the cochlea, but we should get some more EEG in there.
Yeah, definitely.
Yeah,
let's do that.
Thank you.
And I want to mention next week we'll have Simon presenting chapter 2, if I remember correctly, right? And,
that's right, mate.
That's probably the lightest weight chapter in the book. It's on theories of hearing, so you'll have to work to make it fun, Simon.
I'll do a bit more Kuhnian approach to some of the exposition there. I want to thank Dick. You certainly didn't disappoint, mate, and I think you've provided a very rich and nuanced introduction to the book and to the lecture series as a whole. And I'm sure that this is going to provide the motivation all to put aside 1 hour for the pre-read for each chapter, and then to log in and hear the lecturers and join in discussion and Q&A. I'm going to publish the list, the program of lectures and lecturers on the email list the next day or two. And we have about 50% of the lectures covered, and I'll email some of you directly to see if you're willing to lecture for one or so of the chapters. And of course, if you're interested in presenting a particular chapter, please reach out to me, and we can insert you into the program. We're always on the lookout for enthusiastic lecturers. So again, thanks, Dick. That was a fabulous introduction, mate. And I'm really looking forward to the progression through the book.
Yeah, if we can stop the recording, I'll hang around as long as anyone wants to chat informally.
Okay, that's fabulous.
Thank you all for coming.